Hello, this is problem set number 2, problem 3. For part A, calculate the specific heat at constant volume of water vapor, assuming the nonlinear triatomic molecule has 3 translational and 3 rotational degrees of freedom, and that vibrational motion does not contribute. The molar mass of water is 18 grams per mole. Okay, so let's start with our givens. Got water vapor, and we know that translational degrees of freedom, we've got quantity 3, right? And for rotational degrees of freedom, we also have quantity 3. And they said for vibrational degrees of freedom, that in this case, vibrational motion does not contribute, so we've got 0. Okay? So in total, we've got 6 degrees of freedom. 6 degrees of freedom in this problem. Okay, and it was also given that the molar mass was 18.0 grams per mole. All right. Okay. And we know the additional heat capacity per mole due to each degree of freedom for a constant volume, right? So for a constant volume, each degree of freedom has an additional heat capacity per mole of 1/2 R. Okay. And I got that from the notes. That was from lecture notes. So therefore, the heat capacity in total is equal to X over 2R, right? This was a formula from notes. This is an important formula, right? And this is the molar heat capacity. Molar heat capacity. This is the universal constant, R. And X is our degrees of freedom. Degrees of freedom. Okay? Also, in the previous, for problem number 2 and problem set number 2, I mentioned that R is equal to 8.31 joules per mole times Kelvin, but it is also equal to 0.08206 liters times ATM over mole times Kelvin. Okay, so these two are equivalent. It just depends on the problem which unit you want to use, whether joules per mole Kelvin or liters times ATM per mole Kelvin. Okay. And I know that the unit for my molar heat capacity right here, CV, the unit for unit of capital CV is joules per mole times Kelvin. So therefore, I will use this version of R in this problem, okay? But it's good to know both of them. On your cheat sheet, you should definitely have both of them. Okay, so moving on, let's calculate for the molar heat capacity. Okay, I know in total I have 6 degrees of freedom, right? So 6 degrees of freedom, that is my x is equal to 6 in this problem. So I'll just plug that in. So my molar heat capacity is equal to 6 over 2 R, right? And that is going to be 3 times our given R right here, which is 8.31 joules per mole times Kelvin. Okay, so that comes out to the molar heat capacity is equal to 24.9 joules per mole times Kelvin. Okay, and I know that that's the molar heat capacity right here because of the units, right? So molar heat capacity and I know this because of the units. And I'll expand on that a little bit in a few. I know this due to units. So what do I mean that I know that this is the molar heat capacity because of the units? I'm talking about these units right here, right? Joules per mole times Kelvin. So this question is asking for the specific heat, right? And I've got the molar heat. So what is the difference between specific heat and molar heat? Okay. So difference, difference between specific heat capacity and molar heat capacity. Okay. In chemistry and physics, so in physics, specific means per unit mass, okay? So per unit mass, probably per kilogram or something like that, right? And molar mass, or molar, means heat capacity. Molar heat capacity is the heat capacity per molar quantity, right? Per molar quantity. And as I can see here in the units, I've got moles right there. So that I know that's molar mass or molar heat capacity, right? Because it's the heat capacity per molar quantity. Okay? So I just wanted to clarify that. That's how I know that this is the molar heat capacity. So actually, the units for specific heat capacity is joules per kilogram Kelvin. And for molar heat capacity, the unit is joules per mole Kelvin. And as you guys can see, the only difference is specific is per unit mass. See the kg right here, right there, kg. And for molar, it's mole, joules per mole times Kelvin, right? Okay, so anyways, back to the problem. So right now I have the molar heat capacity, okay? How do I convert that into specific heat capacity? Okay, so the relationship between molar heat capacity and specific heat capacity is given by this formula, or this equation. So CV equals molar mass times little cv, okay? I'll also encircle that in red, put a red box around it, because that's quite an important formula. And basically this guy, capital C, that is the molar heat capacity. This is the capital M is the molar mass. Okay. And small c is specific heat capacity. Heat capacity. Right? And right now, I was able to solve for my molar heat capacity. And up here, we were given M, which is capital M, which is a molar mass. So now, as a question asks, calculate the specific heat capacity, and I could find that out, right? Just, that's this guy, okay? So let's do that. Okay. So using this equation, my CV I calculated to be my molar heat capacity, capital C, I calculated to be 24.9 joules per mole times Kelvin is equal to my capital M molar mass, which was given up here. That's actually given in grams per mole. I'll convert that to kilograms per mole. And that would be, just converting grams to kilograms, that's 0.018 kilograms per mole. Okay, so that's the value of my molar mass. So 0.018 kilograms per mole. And I am looking for my specific heat capacity, which is tiny c, small c, okay? And so if I plug that in my calculator, I would find that my specific heat capacity is equal to 24.9 joules per mole times Kelvin divided by 0.018 kilograms per mole, which is specific heat is equal to 1,380 joules per kilogram Kelvin. So that is the specific heat capacity right here. This is the specific heat. That's the final answer for part A, okay? And again, I'll just reiterate the difference between specific heat capacity is per unit mass, so that's the units, which we see here, and molar mass is the heat capacity for molar quantity, and this is the units, which we see here. And we could solve for one or the other based on this formula right here. So that is the relationship between molar heat capacity and specific heat capacity, is this guy, okay? Okay, I'll clean up my notes. All right, so moving on to part B. This was part A. Okay, and part B. The actual specific heat of water vapor at lower pressures is about 2,000 joules per kilogram Kelvin. Compare this with your calculations and comment on the actual role of vibrational motion. Okay. So they said that the specific heat capacity, the specific heat of water vapor at lower pressure is about 2,000 joules per kilogram Kelvin. Okay, so tiny c at lower pressure is actually about 2,000 joules per kilogram times Kelvin. Okay. And they wanted me to compare that with compare with your calculations, right? And comment on role of vibrational motion. Okay. So this is, right now I've got the specific heat at lower temperatures for water vapor. So I'm just gonna change that into my molar heat capacity. And I know I can do that by this formula as we talked about, right? So I'll just plug that in. This is for lower temperatures. My molar mass is 0.018. 0.018, yes, kilograms per mole. And my specific heat is 2,000 joules per kilogram Kelvin. And so I'll find my molar heat capacity at lower pressures to be equal to 36 joules per mole times Kelvin, okay? And so here I have, what color? Let's use bright blue. Okay, so here at lower pressures, I've got 36 joules per mole Kelvin for my molar heat capacity. And earlier, when we were looking for the molar heat capacity, given the assumptions that we had 3 degrees of freedom in translational, 3 degrees of freedom in rotational, and that vibrational motion had 0 degrees of freedom, right? It didn't contribute earlier. So let's compare that with part B. So earlier we had 24.9 joules per mole K right here. So, oops. So at lower temperatures, lower pressure, okay, we got 36. So I'll just write that down. So at lower pressure, we got 36 joules per mole K, which is what we solved for in part B. And then let's subtract that with this guy from part A, minus 24.9 joules per mole K. And that would equal 11.1 joules per mole times Kelvin, okay? So that's a difference. This is a difference in, this is a difference in molar heat capacity, okay? And again, I know that right here, right? For a constant volume, each degree of freedom has an additional heat capacity per mole of 1/2 R, right? So I use this formula. So I'll use that formula again, this guy, to find X, or the amount of degrees of freedom, right? So 11, I'll write that down first. Okay, so that's molar heat capacity is equal to X over 2R, right? And we said this is what we're looking for, right? This is the degrees of freedom. So 11.1 joules per mole times Kelvin is equal to X over 2 times R. R is, what was R? 8.31. 8.31 joules per mole Kelvin. Okay. So solving for solving for x, right? I would get x is equal to 2.7. So this is the degrees of freedom. That's a difference of degrees of freedom, right? When in the actual specific heat of water vapor versus when we assume that vibrational motion does not contribute, right? So that's significant, right? That's a significant amount. And so we could conclude that therefore vibrational degrees of freedom play an important part, right? Play an important role in heat capacity, okay? In heat capacity. And when we say heat capacity is really just the number of heat units needed to raise a temperature of an object by 1 degree Celsius, right? So heat, I'll just mention that just in case somebody needed an explanation for that, but heat capacity is the number of heat units needed to raise the temperature of an object by 1 degree Celsius, right? Okay. But yeah. Basically, this was our answer for part B. Okay, hope that helped.